just repeat a little bit, just mention the main points of these. So a mixed ensemble just means that we have a set of quantum systems, identical quantum systems, but they can be in different states. So some fraction of the systems in a certain state and another fraction in another different state, and so on. So the density operator characterizes this ensemble, and it is given by this expression here. So Wi is the weight or the fraction of the quantum systems in state psi I. And the sum of the weight must, of course, be equal to 1. And the important point to note here is that the states themselves need not be orthogonal. So they are normalized, but they are not orthogonal. So the states are normalized because these are quantum states, so they are normalized as usual, but they do not have to be orthogonal. So this means that the number of states m, so the number of states m here can be larger or can be anything. So it can be much larger than the size of the Hilbert space. So m is really arbitrary. So if we have a pure ensemble, then m will be just equal to 1, and the weight is equal to 1. So it is a kind of more generalized way of treating quantum systems. So we also worked out the ensemble average, how to calculate the expectation value of an observable. We have a mixed ensemble, and this is given by the trace of the density matrix times the operator. So we have it here. So this is a general formula for calculating the ensemble average. So the interesting thing here is that because it is a trace, then it is independent of the choice of the base factors. Of course, the ensemble average depends on the eigenvectors of A, in the sense that A can be written as sum of the eigenvectors. So it will be like that. But the trace itself is independent of the choice of base factors, so we can calculate it in any base factors, as long as the set of the base factors encompass or span the Hilbert space in which the density operator is defined. And then we give an example to illustrate the difference between a pure ensemble and a mixed ensemble by considering just a simple case of a spin half. Okay, so that's what we did last time. So we continue. So let's look at the properties of the density matrix. So one of the important properties of rho, the density matrix, is that the trace of it is equal to 1. So let's show this. Let's go through the derivation. So I have it also in the notes. So this we define to be I from 1 to n, the weight. So that's the definition of the density matrix. Now we take a trace of this. Then we have sum of I to n. And I can introduce a set of base factors. I call it A in the notes, but doesn't matter. So these are now numbers, so we can reorder things. So we then get change. So this is just a property of a trace that you can reorder the quantities inside the trace. So this is just one if we sum over j. So then this becomes sum over I, 1 to m, the weight I, and overlap of the state speed itself, psi I. But these are states, so then it's normalized to 1. So then this becomes sum over the weight, which is equal to 1. So the trace of the density operator is equal to 1. Yes. So if we have a pure ensemble, it has also a special property, because for a pure ensemble, sorry, what am I doing here? Okay. So for a pure ensemble, then the density matrix will be just given by the following projection operator. So we have just one state, psi. So then it is clear that if we calculate rho squared, then it will be just equal to psi. Psi, so that is then equal to rho. So then the trace of rho squared is equal to the trace of rho, so then it's equal to 1. So this is, it's called idempotent. Now there is an important property. It's not the important property of this density operator, is that its eigenvalues are positive definite, and they are always less than or equal to 1. So let's try to show this. So you want to show that the eigenvalues of the density operator are positive definite and less than 1. So let's look at density operator, and then we calculate the matrix elements of this in some basis, and then we diagonalize this matrix. So we have matrix element rho. So it shouldn't be a hat here. It's just so this is the matrix elements of the density operator. So the density operator is, by the way, Hermitian, so that's kind of clear from the definition. So the eigenvalues must be real. So we calculate this thing. So this can be done by a certain choice of base vectors, and then we diagonalize it. So we get a set of, so we diagonalize this. So we diagonalize this matrix. So the size of this matrix is determined by the dimension of the Hilbert space, not by M, not by the number of states in the definition of rho. So we diagonalize this, that will give us a set of eigenvectors, coordinate chi alpha, and eigenvalues E alpha, like this. So I'm following my notes here. So then we know that if we have these eigenvectors and eigenvalues, we can express the density matrix in this way. So that's a general expression for an operator chi alpha, like that. So now let's have a look at density matrix in general. So we get M, it's just a definition of the density matrix. So each of these states can be expanded in the eigenvectors of the density matrix. So we can write it sum over alpha and beta, because we have two states here. So we have Wi, and then we have chi alpha. So I'm expanding the first one here with some coefficient like that, and then we expand the bra. Give me Ci beta dagger chi beta, like that. But we know that these are the chi alpha and the chi beta, they are eigenstates of rho, so they diagonalize the density matrix. So then the beta must be equal to alpha. So then we get sum over I 1 to m alpha 1 to m. We get Wi like this. Then we can identify, if we compare it, this to here, then we can identify E alpha to be equal to sum over I 1 to m weight alpha. But this is C alpha squared, like that. So then the whole thing becomes bigger than equal to 0. And we also know that the trace of rho must be equal to if you look at this expression here, that is just then equal to sum over alpha from 1 to n of E alpha, and that is equal to 1. So then it follows from this too that the E alpha must be first of all positive, and because of the fact that the sum of this is equal to 1, then it has to be less than or equal to 1. So this shows that the eigenvalues of the density operator are positive definite and less than 1. So if we look at this expression here, this then tells us that the E alpha, the eigenvalues of density operators, can also be thought of as a fraction of an ensemble in the state chi alpha, because that's how we define the density matrix. So what's going on here? Yeah. I keep touching wrong button. Things suddenly changes. Okay, so this is the meaning of these eigenvalues. So we can think of the eigenvalues of the density matrix as the fraction of um, systems in state chi alpha. And this will be relevant shortly when we make a connection to quantum statistical mechanics. So the density operator is a very important quantity in statistical mechanics, in quantum statistical mechanics. So that also shows here that if we look at the trace of rho squared, so I just finished this. So that then if we use this expression here, then it is just equal to sum over alpha, so 1 to n of squared. So that also obviously must be equal to or less than 1, because the alpha is a fraction. So the square must be even less than the alpha. So the E alpha. Yes, because E alpha is a fraction. So that shows that the maximum value of the trace of rho squared is then equal to 1. Okay. So the most important point here is that in the eigenvalues of the density operators are positive definite, so they're like probability. So they tell us the fraction of the system if we think of it as the states in the ensemble. I mean, the eigenvalues would represent the fractions of the state chi alpha in the ensemble. So let's look at the explicit form of the density matrix. Let's start with a pure ensemble. So in the pure ensemble, we just have one state. With weight equal to 1, of course, because that's the only state. So then that state must also be an eigenstate of the density operator, because this is equal to times n, and that is equal to 1. So psi is an eigenstate of the density operator with eigenvalue 1. Yeah. So then we look at the matrix of rho. So it's a matrix, it's not an operator here. And we see that it has the following form. So we only have one state, psi. If we diagonalize the density matrix, then it must look like the following. So we have 0, 0, and somewhere there will be 1, and then 0, 0, 0, 0, like this. So that's because there is only one state with weight equal to 1, corresponds to this state psi here. So all the other states must be orthogonal to this state psi. So the eigenstates of the density matrix must be orthogonal to the state psi, and must have so eigenvalue 0, because we know the trace of rho is equal to 1, and the eigenvalues must be positive definite, so we cannot have any other choice than 0. Yes. So this is how the density matrix looks like for a pure ensemble. If we look at a completely random ensemble, completely random. By completely random, we means then that all states in the Hilbert space in which the density matrix is defined has equal weight. Yes. So let's say any given values. Alpha. So chi alpha here is the eigenstates of rho. So then this is equal to 1 upon n, because this forms a complete set of states. So then we have just the unit operator here. So we then calculate the matrix corresponding to this density matrix. Well, then it will be just 1 upon n. This like 1, like this, just a unit matrix. So there's a 0 here, because it's just a constant 1 upon n. And it's independent of how we calculate this matrix. So we can choose any orthonormal base vectors, and it will give us same matrix, provided the bases are orthonormal, of course. Okay, so before we consider the connection to statistical mechanics, would like also to look into the time evolution of this density operator. Evolution. Time evolution of rho. So let's say that at a certain time, let's say t equals 0, you can always choose the time to be equal to 0. So we choose that. And we have density matrix. That's not density matrix, but density operator. It's given by that. And psi I are some states that we choose. So the states, each of these states will evolve in time. So we know how to do this. We just apply the time evolution operator. So the time evolution operator is rather convenient for writing this kind of expression. So we just apply the time development operator as Hamiltonian of the system times t and times psi I here. So then if we use it to figure out the time development of the density operator, then it evolves according to this expression here. So we just use this state here. So it becomes to the minus 4 t psi I e to the I divided by h bar h t, like that. So I just replace these states with this one here. So this is how the density operator evolves in time. So we can look at the equation of motion by looking at the time derivative of these. So the time here, well, it's just taking the derivative of the exponential. So you will get then two terms. Okay, let me write it down. Like this, I have omega I can take it out. So I take the first derivative here, that will give me minus h bar h hat here. Okay, and then another term coming from that one. So that will give me plus to the minus h, like that, on square bracket. Well, this whole thing can be just written as minus I h bar, just a commutator, rho t, like this. It's because each of these is just our rho t. So it looks a bit like the Heisenberg equation of motion, but it's not quite because we have a minus sign here. So we have to keep in mind that we are not in the Heisenberg picture. So we are looking at in the Schrödinger picture. So we just evolve the states according to this time evolution operator. So here rho is not in the pseudo T here, I should say. It's not in the Heisenberg picture. So that's why we have a different sign here. So minus, not positive. So this is how the density operator evolves in time. So it fulfills equation of motion. So actually, if you do in classical mechanics, there is a similar expression for the density operator. That would refer to the density in phase space. And this would correspond to the Liouville's equation. So just a comment here. Liouville's theorem, or equation, whatever you like to call it in classical mechanics. Okay, so this is some fundamental properties of the density matrix, density operator. So now I would like to make a connection to statistical mechanics. So the density operator then plays a very important role in quantum statistical mechanics. It's an essential quantity. So let me see. Okay. So the connection to statistical mechanics is that the entropy, which is also a very central quantity in thermodynamics and statistical mechanics, can be written in the case of quantum system in the following expression. Let's see this expression here. So it's given by minus the Boltzmann constant, KB, times the trace of rho log rho. So how do we calculate this trace? Well, we just use the eigenvectors of the density operator. So we calculate the trace. We insert or call it n here. Then we just replace rho with the eigen values of the density operator corresponding to chi n. So then we just get like this. So just recall that, I mean, if I have a function of operator A, and I want to look at how it acts on a certain state, then we just insert complete set of eigenstates of A. Like that. And this one acting on the eigenstate AN, that just gives me FAN. Like that. Okay, so this is what we have done here. So if we look at this expression here, that reminds us of the definition of entropy in statistical mechanics. So in statistical mechanics, we define the entropy in the uneven new page here, into minus KB sum over I pi, no, pi like this. So if we recall our statistical mechanics course, then we realize that the entropy is given by this expression here. And the pi is the fraction of ensemble in microstate I. Yes. So it's really uh, uh, very similar to what we have. Quantum case, we have minus KB and then sum over I, rho I, log rho I, like this. So as we said before, the eigenvalues of the density operator, so this is the eigenvalue of rho, gives us the fraction of the ensemble or the systems in the ensemble in the eigenstate chi I. Yes. So instead of microstates, we have quantum states in the case of quantum statistical mechanics. But the definition of the entropy itself is the same. Yeah. So the concept of entropy is the same in the classical and quantum statistical mechanics. It's just that we speak about quantum states instead of microstates, as we do in the classical statistical mechanics. So let's just check that this definition of entropy kind of agrees with the concept of entropy. So if we look at the pure ensemble, so there is only one state. Then there is only one state, so and the eigenvalue is equal to 1. So that then means that the entropy is equal to 0 because rho I, where there is only one I here, is equal to 1. So then it's log 1 is 0. So then the entropy is 0. So this kind of fits with the concept of entropy as a measure of randomness. So we have a pure ensemble. Well, there is only one possible state. So it's the most ordered state. On the other hand, if we look at the completely random ensemble, then we have S equal to minus KB. As we said before, the eigenvalues are all equal to 1 upon n, log 1 upon n. So then this is just equal to KB log n. It's because this sum here goes from 1 to n. So log n is actually the largest entropy we have. So it's a completely random system. So it fits with our picture of entropy. So what we want to do now is to work out the expression for the density operator. So density operator for assembler for an assembler. Maybe I should put the N there for an assembler in thermal equilibrium. So we have in mind here is a system, an assembler, that is in contact with a heat bath. So we have a system for an assembler. So contact with heat bath. So this kind of system is usually called the canonical assembler. So we are not doing statistical mechanics here, but I think you learned this in statistical mechanics course. This canonical assembler is called. So what we want to do is to find an expression for this density matrix for the assembler in thermal equilibrium. Now, in thermal equilibrium, it means then that the density operator does not change with time, because that's what we mean by equilibrium. So this is in equilibrium. So this implies that the commutator of the density operator with Hamiltonian is equal to 0. So that comes from the equation of motion that we just worked out previously. So because h and rho commute, this implies that we can choose the eigenstates of h to be simultaneous eigenstates of rho. So I can choose eigenstates of h to be simultaneous. Eigenstates of rho. Yes, because of this commutativity. Okay, so if we do that, so we say that we have h psi k, so that the eigenstates have k, eigenvalue k. Then we say this is also an eigenstate of rho with eigenvalue rho k. Okay, so this is the first step in the derivation. So we can express rho in terms of its eigenvectors and eigenvalues. So we can write it in general in this way. So as we said earlier, we can then think of the eigenvalues of the density operator as the weight. So if we compare this with the general definition of rho, so we can think of the eigenvalues as the weight or the fraction of the quantum systems in the ensembler to be in the state labeled by psyche. Okay, let me look at the time. Okay, so maybe we can have a break here. It's could be a good time to have a break because it's going to be quite lengthy in the next step. Okay, so maybe we will have a break at this point. So, can any questions up to now? Okay, with no questions, then we can meet again at say a quarter past. Yes, so let's continue with the derivation of the density operator for an assembler in thermal equilibrium. This is in contact with a heat bath. Yes, that's our goal. So, according to the laws of thermodynamics, a system that is in equilibrium, in thermal equilibrium, and tends to maximize the entropy under the constraint that the average, the ensemble average of the energy, the Hamiltonian, is given. So under a given internal energy. So S is maximized under the condition that, so this is the trace of rho h. So that's the ensemble average of the Hamiltonian. So that's equal to sum over. So when we take the trace, we can use the eigenvectors of H, which are also eigenvectors of rho. So then this just becomes sum over k from 1 to n. That's the number of states. Okay. So we call this, let's say U. That's usually called U. So that is given. It's fixed. Given U. So we now want to maximize the entropy under this condition here. The internal energy, so this is called the internal energy. Internal energy is given. Yes, and a prescribed value of the internal energy. Then, of course, we also have the condition that the trace of rho, which is sum over k of the eigenvalues, must be equal to 1, because that's just the sum of the probability of fractions, and then that must be also fixed. Sum is equal to 1. So let's now look at the entropy or Hamiltonian. So what we want to calculate is we want to vary the entropy under this two condition here. Under this two condition here, let me see, 1 and 2, under the given internal energy and the constraint on the eigenvalues that they have to sum up to 1. Under these two constraints, we want to maximize the entropy. So we want to say this is equal to 0 under these two conditions. So if we look at the change in the ensemble average of the Hamiltonian, so that is then equal to sum over k to n delta rho k. Okay, so that's equal to 0. Because the energy was are given, so those are the eigenvalues of the Hamiltonian, so we cannot change those eigenvalues. But the population can be changed, so that's what we want to figure out. Yes, so delta rho case is something non-zero, and from the, so this is from 1 here, and from the normalization condition here, the second one, then we get a delta of trace of rho. This changes as sum over k. There, okay, is equal to 0. So 0 because we fix. Yes, so it does not change. So this the condition here can be conveniently incorporated when maximizing the entropy by using the Lagrange multipliers. So we do that. So what instead of maximizing the entropy S, we consider another quantity S, and then we introduce the Lagrange multiplier. We call it beta KB like this, H, and then minus gamma KB, and the trace of rho. So these two are the Lagrange multipliers. So we incorporate the constraints into S prime. So these two constraints here, we include them in the new quantity S prime. Then we can require that delta S prime is equal to 0 without worrying about the constraint, because we have already included here in S prime. Yes, these two constraints. So that's the purpose of the Lagrange multipliers. Okay, so let's calculate one by one this term here. So we calculate ds. So that would then be the minus kb sum over k to 1 to m delta rho log rho k. So just write this down again. Sum over k, k log rho k. Yes, so that's the s. So then we get two terms, one from here and one from the log. So then we get plus rho k, but the derivative of log is 1 upon rho, and then delta rho k. So that gives me minus kb sum over k. So I just call it sum over k. We understand it goes from 1 to n. And delta rho k, rho k plus 1. Okay, so that's the s. The h we have already worked out, so that is equal to sum over k delta rho k ek, and delta trace rho we have also worked out, so that is sum over k delta rho k. It's equal to, that's what we have here. So then we just plug this in into the S prime. So delta S prime is then equal to sum of these three here. So that gives me sum over k, delta rho k, and then I have log rho k plus 1. So that is from ds here. I have taken out the kb because all these terms have kb. Yes, that's why there's the kb is introduced in the Lagrange multipliers. So the kb disappears because we're going to set this equal to 0. And then from the dh we get plus beta ek. So that's from this term here. And then we get gamma. So that's what we get. So this is equal to 0. So that is ds prime. Then we say that, well, this variation, delta rho k, is an arbitrary variation. We have not specified what that is. It's an arbitrary variation. So then it should be, this quantity here should be equal to 0. Yes, because delta rho k is a general arbitrary variation. So then we can solve for rho k. So that becomes exponential minus beta k minus gamma minus 1, like that. So beta, gamma, and gamma are the Lagrange multipliers. As you might guess, this beta is related to the temperature. So actually it's 1 upon temperature, as we'll see later. Now the constant, so I can write it like this. Okay, times some constant equal to minus gamma minus 1, like this. So this constant here is determined from the condition that sum over. So let's see if I can write this. So determine, and then I begin read this. Determine from the condition that the sum over k of rho k is equal to 1. Yep. So if I sum to 1, that will give me the constant. Yes. So if we do that, then we find the solution. So we get then rho k, this is what we want, is equal to minus exponential minus beta k divided by what is called the set partition function. So that is equal to the trace of equal to sum over I, let's say, of e to the minus beta ei. So you recognize that this is just the Boltzmann distribution function. So it tells us that this rho k is just the fractions of populations in the ensemble, which has energy Ek. So they are in the states Ek. These are just the fractional population. Fractional population with energy Ek. So this is exactly what we usually call the canonical ensemble. So this is the canonical ensemble in statistical mechanics. So the canonical, as you know, there are 3 types of ensemble. There's the micro ensemble. Then there is the canonical ensemble, and then there is also the grand canonical ensemble. So the microcanonical ensemble corresponds to some closed systems with a given energy, volume, and particle numbers, whereas the canonical ensemble corresponds to an ensemble in contact with a heat bath, so for a given temperature, volume, and particle numbers. And if you do grand canonical ensembles, which we don't do here, then you will also allow for the particle numbers to fluctuate. So you have an open system in contact with the reservoir. Um, uh, so the heat and the particles can be exchanged with the reservoir. So here we are talking about the canonical ensemble that's given raised by the Boltzmann factor. So that we can deduce that our density operator is given by this expression here. So that's the final results. It's quite nice, I think. This is the corresponding quantity in quantum statistical mechanics. We work with the operator, the density operator. It's the canonical, as for canonical ensemble. So let's work out some example. So let's consider the ensemble average of an observable corresponding to an operator A, let's say. So then the ensemble average is given by trace of rho A. It's according to the general formula. Then it's given by 1 upon Z sum over K of e to the minus ek. It's beta here. Okay, so we have taken the trace by using the eigenvectors of the Hamiltonian. So AK here is equal to the expectation value of the operator A in the eigenvectors of H. Okay. So this is the quantum mechanical version of the ensemble average. So you have a similar expression in the usual statistical mechanics. You weight each value here with the probability. So I put it the Z here, maybe that's clearer. So like this. So this gives us the probability of the state in the state labeled by K. Yes. So for example, if we look at the internal energy, this U, so that would be the ensemble average of the Hamiltonian. Well, that is just 1 upon Z sum over K minus P Ek times Ek, like that. So that can be also be written as the derivative of the partition function. So Z here I should have said that. Z is the partition function here. the central quantity in statistical mechanics, of course. So you can see that this beta is just the inverse temperature. So beta can be interpreted as inverse temperature. So the temperature is really just the Lagrange parameter that is associated with the energy. So it should be there's a KB here actually. I'm used to setting all the constants equal to 1, but here you should have the KB also, so that's the KBT. So let's have a look at what happens when we are in the very high temperature case. So in the limit of a very high temperature, look at this quantity here. So in the limit of high temperature, it would imply that beta goes to 0. So I just need a little space here. So high temperature. Temperature corresponds to beta goes to 0. Then from this expression we can see that the rho k go to 1 upon n. Yes, because the z becomes just n, because the z is just a sum of over I, so that goes from 1 to n. And the exponential, all this exponential becomes just 1, because beta goes to 0. So that again fits with our understanding of entropy. So at high temperature, the systems become very random. It's the most random case. So then each state is equally populated with these fractions, 1 upon n. It's a very high temperature limit. Yeah. And you can also see that at a very low temperature, so that would correspond to the beta goes to infinity, then the system goes to the lowest state, so that would be the ground state, and there is only one which is occupied. So the population is 0 everywhere else except the lowest state. Yes, so low T, it would mean that large beta, and only lowest states are occupied. Okay, so let me see. We have, let's see, 20 minutes. So let's do some more concrete example. So let's consider harmonic oscillator. So this is an example. So we have a harmonic oscillator. So then our Hamiltonian is equal to, so we want to do some statistical mechanics for particles under parabolic potential. So I will not go through all these derivations, but you already know. So then the important thing is that the energy eigenvalues, this harmonic oscillator is given by of h bar omega. This is what we need to know. So the first thing to do, whenever we do statistical mechanics, one of the first things we want to do is to compute the partition function. The partition function is really the central quantity in statistical mechanics. Partition function, so that's the z, is given by sum over n here. So n here labels the eigenvalues. So now we have 0 to infinity minus, so these are just the states and it's available. So that is equal to so half h bar omega. So I can take out the terms which does not depend on n, so that gives me minus beta omega upon 2, and then sum over n e to the minus n beta h bar omega. So this can be summed analytically, because if we just call it x in the notes here, we call this exponential x, then these are just sum of polynomials. So this goes from 0 to infinity, so then the first term will be just 1, and then x, and then x squared, and so on. So we recognize that these are just 1 minus x minus 1. So then we get the well-known partition function here. One minus x, so that would be to the minus beta h bar omega. So that's our partition function for the harmonic oscillator. So let's look at internal energy. In the two limiting cases, so we look at the high energy limit and not the high energy, but the high temperature limit, I mean, and then we look at the internal energy in the low temperature limit. So for the high temperature limit, so that means the beta small, close to 0. We do this by rewriting z partition function as 1 upon 2 psi. So this is just a straightforward algebra. You can just check this. So you can rewrite the partition function in this way. What you do is just you divide the denominator by the numerator, and then you realize that is just sine of beta h bar omega divided by 2. So we calculate internal energy, so that we say it's given by derivative of the log of the partition function. So this is statistical mechanics. So that is then equal to d by d beta of log sine and h bar here. So the log 2 of course disappear, does not depend on beta. So, and also we have a minus sign because the sign appears in the denominator, so that gives me a minus sign. So that's why it becomes plus here. Okay, so now we can calculate this log sign. This is just again the algebra. So we'll calculate the derivative of this with the beta. And let me not spend too much time on the algebraic details. So let me just write down the final answer. So that is given by tangent, hyperbolic tangent, 1 upon hyperbolic tangent of 2, like that. So this is what you get when you take the derivative. It's just a little algebra. So we can make an expansion in small beta. So expand in small beta. Small beta expansion. Then the u becomes h omega upon 2 plus beta and so on. So let's clean this up a little bit so to make it nicer. So that becomes 1 upon beta plus I have all this in the notes, so I'm just following in my notes. Anyway, I did it step by step, so you know what's going on here. So this is the expression for the internal energy for small beta, means high temperature. And this is indeed what we would expect from physical consideration, that the internal energy is given by kBT. So this is kBT plus some higher order terms. So we know that from classical thermodynamics, at very high temperature, then we can determine the internal energy to be equal to just kBT. So that fits again with our usual understanding of an assembler for the high temperature. We can also, so this is this high temperature expansion. So let's have a look now at the low temperature. So we want to work out the low temperature limit. So low temperature limit means a large beta, because beta is inversely proportional to the temperature. So we just calculate u again. That is given by d beta log z. So we plug in what we had for z before. So the z is equal to the minus beta h bar. Looks very messy here. Beta h bar, yeah, 2 divided by 1 minus Okay, so we just take this derivative, so that becomes d by d beta. And so we get we take the log, then we get take the log of z, then we get 1/2 beta h bar omega. So that's from the numerator, and then we get log of 1 minus e minus beta h bar omega from the denominator. So we can easily calculate this. That gives me half omega divided by minus 1. So we recognize that for large beta, this will go to 0 because beta becomes very large. So the denominator becomes infinite, so then this goes to 0. So I shouldn't say equal to, but goes to 0 at low temperature, at low T. So large beta goes to infinity, let's say. Then the second term disappears. Then we end up with a 0-point energy. It's a very low temperature. So again, it fits with what we expect from physical consideration. Okay, so that is an example of the use of this density matrix. Yeah, so this is a central quantity in quantum statistical mechanics use the density matrix, density operator. So whenever we have an ensemble, we should use this formulation. So it's quite different. Yeah.
I'm a bit confused as to, for the high temperature, why the energy wasn't 1/2 kBt, since it's only one-dimensional harmonic oscillator.
So this is for the low temperature. You mean the previous one?
Yes.
I think it should be just kBt, right? I mean, maybe I missed the factor of half. That's possible. Let me see.
But there are 2 quadratic degrees of freedom, right? In Hamiltonian.
Yeah, sorry. Let me see. Is that true? I mean,
But shouldn't it be kBt then?
kBt, that's what I thought. But you were saying that it should be 1/2.
I wasn't thinking about the derivation, more of that it's a one-dimensional system.
Mm-hmm.
And then since there's only 1 degree of freedom, then that the energy would be 1/2 kBt, since in 3 dimensions, 3/2 kB.
Okay. It could be that I missed something half here.
Or maybe I'm just drawing parallels where there shouldn't be parallels.
Okay, I have to, I don't know if I can answer that on top of my head here, but the derivation seems to give me kBt, which seems to be correct, but you were saying that?
I guess you're talking about the average kinetic energy of gas molecules at high temperature.
Mm-hmm.
And I think this is not the same. But yeah.
Okay, yeah.
Yeah, I mean, we have 2 quadratic degrees of freedom, right? The momentum and the spring tension.
Yeah.
So I think by the equipartition theorem, it should be 2 times 1/2 kBt, right? So it should be kBt, I think.
Yeah.
I think it makes sense that it should be kBt.
Maybe you're talking about kinetic energy, and you have the 3/2 kBt.
Yeah, okay. So I think I understand where I got it wrong then. Thank you.
Yes, it's the internal energy, yes. Okay, that's good. Yeah, I think I have checked this algebra. It should be correct. Yes. Okay. Are there any questions? Yes. Okay. So let's see. We have just less than 5 minutes left. Okay. So if there are no questions about density operator, we can continue a little bit. Going back to the angular momentum, and we continue next time. But let me talk a little bit about this rotation operator. So we are back to angular momentum. It's a long topic. So we want to find representation of the rotation operator. So you recall that we have this rotation operator. And phi like that. So I just call it R. It's a rotation around the axis and by angle phi. So there are an infinite number of representations for this. So I should come with representations of this rotation operator. So we already know that in 3 dimensions, we have a set of orthogonal matrices. So 3 by 3 matrices. So that's one particular representation of the rotation operator corresponding to rotation in real space. So if we think about it in terms of the angular momentum eigenstates, those representations, the 3 by 3 matrix representations, actually corresponds to j equal to 1. Yeah? So we want to work out the more general expressions for the representation of the rotation operator. We have also worked it out for the spin half. So there we have a 2-dimensional representations corresponding to j equal to 1/2. Also the dimension of the representation is given by 2j plus 1. So if j equal to 1/2, then we have a 2-dimensional. If j equal to 1, then we get 3. So the 3-dimensional representations corresponds to j equal to 1. So what we want to calculate is this matrix elements here. So this is the matrix elements between 2 angular momentum states. M, like that. So Jm here labels the eigenvector of the angular momentum. Now, you might ask, why is it that we don't have j prime here on the left, but just j? So why is it that the 2 j's, the left and the right, are the same? So the reason for this is because we have this j squared, which commutes with all the J component. Yes. Since the rotation operator consists of the components of J, it's just an exponential of these J dot n, then this rotation operator also commutes with J squared. So this implies that if we apply J squared, so we just write it like this. Putting on Jm, well, that's of course is 0 because it is 0. But this implies that J squared acting on Jm like that is equal to J plus 1 H squared, I think. Yes. Gm like this. So we say that this state here, the rotated state, is also an eigenstate of J squared. So this means that the rotation cannot change the value of J. So this state is also an eigenstate of J squared. So this means that rotation, so they are acting on Jm must be just a linear combinations with the different m components. So we will have something like this. So if I just introduce a complete set of state here, like that. So this state and this state must have the same J. If they are different, then it will be 0 because state labeled by J, when rotated, it will remain in that subspace, same J. So we cannot have matrix element like this. So this will be proportional to delta J prime. Yes, so if the J prime is different from J, it will be 0. Okay, maybe we should continue this next time because we done already over the time. Okay, so we just continue next week. Unless you have some other questions. Okay, if not, then we say goodbye here. And then,
Thanks.
thanks. Have a
Bye.
good weekend.
Thanks. Bye bye.
Yes.
You too. Bye.
Bye bye.